A warm welcome to the 14th session in the third module on signals and systems. We have stated a very important principle. I dare say one of the most fundamental principles of sampling and reconstruction in the previous session. The principle said that a band limited signal, band limited to FM, can be reconstructed perfectly from its samples taken at a rate more than 2 times FM, and we saw why that is the case. Essentially, the imposters can be removed and the original can be retained if we have ensured that this Nyquist principle, namely Fs greater than twice FM, is obeyed. And in fact, the proof of this theorem was constructive in the sense that it gave you a procedure by which you could reconstruct the signal from its samples. Let us recapitulate that procedure, as it is a very important idea that we should appreciate very thoroughly. What we said was that if you had an original spectrum like this, let me draw it again for you. If you had this original spectrum of the signal band limited to FM, let us say looking something like this, and you sampled it at a rate Fs greater than twice FM, copies of the original spectrum would be created at every multiple of Fs. And reconstruction essentially means retaining the original and cutting off the copies. So, we need a system which retains this and cuts off all the rest. Now, how do you do that? Suppose you passed this whole sample signal. So, this is the spectrum of the sample signal. Suppose you pass this sampled signal through a linear shift invariant system which has a frequency response. I am writing the frequency response as a function of the cycles per second frequency, note. And what is this frequency response that we desire? Let us draw that explicitly. The desired frequency response needs to be 1. The desired frequency response needs to be 1. Between just a little before FM, I mean minus FM actually, just a little before minus FM on the negative side, and just a little after FM on the positive side of F. So, here I am writing in terms of the cycles per second or Hertz frequency, and I am saying the desired HF needs to be 1 from, let us say, minus FM minus delta to FM plus delta. Essentially, you must ensure that Fm plus delta is less than Fs minus Fm, strictly less than. So, that is not very difficult to do. If you go back to the previous drawing of the spectrum, you can see that that should be possible. Look at it here. So, this is Fs minus Fm here, and you have this margin, as I pointed out in the previous discussion. As long as you have ensured that Fm plus delta remains within the margin, you are doing well. So, you are essentially saying here that Fm plus delta keeps the cutoff or remains within the margin. Now, let us look at this drawing again of the desired HF. You have Fm just a little before here and minus Fm here. You could have always, one could have argued that you could have kept this desired HF 1 up to Fm and minus Fm, between minus Fm and plus Fm, and then 0 afterwards. But what is the problem there? The problem is that you might have a tonal component at Fm, meaning there might be an impulse in the frequency domain at Fm. When will that happen? That would happen when you have a pure sinusoid. You recall that there are impulses in the frequency domain when you have pure sinusoids. So, there is a tonal component at Fm, and if you make the HF cut off at Fm, you could have trouble with that tonal component. So, you need to keep Fm plus delta as the cutoff. This is an important and a subtle point. In fact, we can understand it even better if we take just that tonal component and focus upon it. So, let me explain this point to you. It is a little subtle and we need to understand it well. See, consider a tonal component. When you say a tonal component, you mean a sinusoid with frequency Fm. Suppose we sample this at exactly twice Fm. So, sampling rate Fs is exactly twice Fm. What is going to happen? Let us see it pictorially. So, you have this sinusoid. Now, this condition Fs is twice Fm essentially means that you have 2 samples per period. Now, that is very easy to see. Suppose for example, your 0 is located here, so you have taken one sample here. The next sample would come at the corresponding point on the negative cycle. So, here, and the next sample would come here and so on and so forth. So, you could keep doing this. So, these would be the samples. Now, suppose you are unlucky and you take the sample where I am showing you in green, you start sampling it here. What would happen? Your sample would come here and then at every other 0 crossing. So, in the unlucky event that you start sampling the sinusoid at a 0 crossing, all your samples are going to fall at 0 crossings. This is where you have trouble when you sample at exactly twice Fm. That is why we said Fs must be greater than twice Fm. This was a subtle point. I am emphasizing that now, because a tonal component at Fm, that is what it is, a tonal component, a sinusoid with precisely the frequency Fm, if not sampled at a rate more than 2 Fm, can have this trouble of all the samples falling unfortunately on 0 locations. And if all the samples fall on 0 locations, there is no way to distinguish between whether you had a 0 signal in the first place or whether you had a sinusoid at all. Now, there is another reason also, and that reason is what we are saying in this business of a margin here. You of course require that margin because you might want to retain this tonal component. There might be an impulse right at the boundary at Fm, and you do not want to cut off, or you do not want the cutoff to fall on that impulse. You want the cutoff to be beyond that impulse, so the impulse also comes in. That is one way to understand why you need, that is another way to understand why you need Fs to be greater than 2 Fm. But there is another more subtle reason which we will now proceed to derive. Let us go back to that frequency response that we drew, the desired HF as we called it. Let us go back and see what it looked like. This is what it looked like. Let us find out the corresponding impulse response. So, the corresponding impulse response can be found by taking the inverse Fourier transform. Let me work out the inverse Fourier transform of this. Let us do that little bit of work, it is very important. All of us are familiar with the expression for the inverse Fourier transform. Essentially multiply the spectrum by e raised to the power j2 pi f t and integrate with respect to f over all regions where the spectrum is non-zero. In this case, the spectrum happens to be 1 between minus Fm minus delta and Fm plus delta. Let us put Fm plus delta equal to Fc. It is a very easy integral to evaluate. Let us evaluate this. This is simply e raised to the power j2 pi ft divided by j2 pi t from minus Fc to plus Fc. A very easy integral to evaluate. Let us simplify this. So, it is e raised to the power j2 pi fct minus e raised to the power minus j2 pi fct by j2 pi t, which is easy to simplify. It is essentially 2j times sine 2 pi fct divided by j2 pi t. And of course, we could multiply and divide by fc and cut off the 2 j's from the numerator and the denominator. So, where are we now? that gives us essentially 2fc times sine 2 pi f c t divided by 2 pi f c t, and that is essentially 2fc times what is called sinc. You know how to write sinc. So, sinc 2fct. You will recall that sinc x is essentially sine pi x by pi x. So, we have derived this impulse response here. Let us sketch it. Where does the sinc function go to 0? It goes to 0 at all the integers. So, sinc x is equal to 1 for x equal to 0 and 0 for all integer x, x not equal to 0. So, sinc of 1, sinc of minus 1 and so on. Now, what are we really saying here? You see, we are saying we have this function which is 1 at t equal to 0. So, if I locate this function at the point of sampling, it picks the sample as it is, and the integers, where are the integers located? The integers located where 2fct is equal to an integer. What does that mean in terms of sampling? We shall analyze this in greater detail in the next discussion. It is going to take us a while to understand what this impulse response is doing, and that will hold the key. In fact, that will say a lot of things about the system that we are talking about too. It will tell us how we are reconstructing the signal from its samples, and it will also tell us something rather disturbing about the system, about the realizability of this system. So, let us wait for the next discussion to look at this impulse response in greater depth. Thank you.